So now in the second programming thing session of this week, I just want to go back a little bit to linear regression again, the simple linear regression, and just try and sort of play with some real data that's available. So there's one reference that I liked a lot, and this website also covers it. It's called Applied Econometrics with R. Most of the code is taken from the website as well. In fact, all of it. I'll just sort of go through it line by line. Let's just try and clear this. Clear the history as well. I'm on the same page as everybody else now. So now first you have to install this package AER. I'll already done that. So it'll take a few seconds. So once you do that, you start the library. And the library, there's a data called data schools. So we can do that. So let's just go and do the same thing we did before. Let's go and do this cable as well. Let's go come down, and then let's try this whole thing. Let's do cable. The library already is installed for me, so I'll just do CAS schools. Let's try this. Let's see if it works. So it gives you the thing, right? It gives you school, county, grades, and students. The first 6 rows, and it gives you data set of the school. So it. Of course, these are the first 3 columns. Of course, there are many more. There's 2 teachers as well. You can just check that as well. So let's go and do a head of CS schools. Let's check what's called there. So it has grades, students, teachers, CalWorks, lunchtime taken, computer expenditure, income, scores in English, how much they got in reading, how much they got in mathematics. And each class, it tells you the number of students and number of teachers. That's what it does, friends. Right. So maybe I'll just do how many are there. Let's say let's go from one first row. How many are there? How many variables are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say 10. Sorry. This should get everybody, I think. Get everybody. Okay, good. Very good. Maybe 14 minutes. This will give you everybody. Goodness. So now I just what I do is I do this student teacher ratio. Let me just make this a student teacher ratio. Student teacher ratio. Do that. Do this. Sorry, what happened to this? Down, and then I come and just check it again. I compute this thing. So what I do is I take the students and I divide by the number of teachers in the classroom. Like that. Then I compute the test score of everybody as well. So test score, I just take it as the average between reading and math. Right? So do that. Let's compute that. We get this. Okay. Let's go down here. Let's just check what the scores look like. So CA school $1 score. Looks like that's a score of everybody, and then STR looks like the student teacher ratio. Everybody in the class. So some are like there are various numbers. So let's try and plot them. Let's do a simple scatter plot of the score versus student teacher ratio and take data, and let's just do a scatter plot. So it looks all over the place now, right? It's like sort of a symmetric thing. So you draw a line, it's going to come. The decimal is going to come in the middle. Right? Let's do that. Let's do a linear model. Let's see what the linear model says. It gives you an intercept of this and a negative slope. So it's going to go down like this in some sense. That's what line gives. Let's go to the plot. The plot should give you, let's do the plot. So plot is this, and then we add line to the model line. So it gives you a line. Like we expected, it has an intercept at 698, somewhere here, and it comes down at like a negative slope down. Very cool. So now let's try and get the, so this sort of gives you a first level understanding of what the least square line is doing. It's just giving you a line that's just cutting through data set. Right? Very good. So now I want to, let's say I want to understand how to measure the fit. Let's go down here. Let's see how to measure the fit. So this what all we did last time. Remember we did this error sum of squares, explain sum of squares as this first one, and then we did this total within sum of squares, we call it thing, and then total sum of squares, and we had R squared as well. These are measures we use to sort of understand how good the fit was in some sense, right? So now, so R squared is going to be equal to the sum of residuals by total sum of squares. Right? That's what's going to be. So what I do is I wrote with let's do model summary now. Model summary. So you do a summary in your model. If you do correct, it gives you everything. It gives you the residual error, the multiple R squared, and just R squared. It gives you all the numbers. But let's try and do it manually. So for the sake of it, let's try and see what to do. How does it look like, right? So if you do a compute, so what am I doing here? SSR is the sum of residual squares. This is total sum of squares is going to be sum of score minus mean score whole square, and then R squared is 1 minus SSR by 2. Let's do that. And let's see what happens. Score not found. Why is score not found? Interesting. Object score. I thought the score was below. No. Interesting. Let me call this. What did I call? I called it something else. I called it like okay, let me call it score. Let me call this a score. And here, let me call it score equal to this. Let me go down here. TSS, and then we go R squared. And then R2, if I do this, I get 0.015, which is exactly what I got here as well. Same. That's what the thing does. Right. Now, let's look at the I'll go compute the SER normally. That's this one normally. So we'll look at n is number of rows, then look at square root of SSR by n, and then SER exactly. That's exactly what happened here. The residual standard error, you get it as 18.58. This is the exact calculation I've done manually. Okay. So this tells you how to do the fit. The fit is 0.12. It's not, I mean, it's not great. It's just 5% of the variance of the dependent variable, right? So only 5% is explained by this by the explainer variable. That's what it means. So the regression explains very little. So it doesn't. It's not a. It's the variance in the score. So this is not a good line to understand student-teacher ratio versus test score. That's what the R square is telling you. Right? It's 0.05. It's not even close to 1. If it's close to 1, then you know it's doing well. So in some sense, this is the first tells you how good the fit is. Of course, you can clearly see the fit is not so great. It's this line in the middle. Very nice. Now I want to sort of do the next thing. I want to test the assumptions. You know, we had what assumption we had? We had mean zero assumption. Then as the first one, let's just try and see how important that is, right? What I'm going to do is I'm going to do some simulate data. So here I just set the seed. That's just a seed to make the results replicable. So if you do it again, it'll come the same way. Because that's if you run the same program again, it'll come the same way. So see this. So what I first do is I generate uniform random variables, samples uniform, 50 samples from -5 to 5. That's what X looks like. Let's turn type what X looks like. X looks like this, -5 to 5 gives you 50 samples. Then what I go do is I just go Y is equal to, I take the errors to be normal with mean 50 and deviation 1. Right? Into that. So let's say you should give you samples from normal random variable with mean 50 and deviation. Then this is how I'm going to generate my Y. Y is going to be X squared, the nonlinear function, X squared, 2X, and U. That's how Y is going to look like. Okay. So Y is going to be quadratic, right? So I do this. So let's say I do a simple thing. Let's go and plot Y and X. Let's do that. So what will I get? So let's do that. So I'll just get this Y. Y looks like X squared minus 2. It looks like a curve length, right? So the correct fit is like someone asking me before as well, that if I do a linear regression to this, I'm not going to get the correct answer, but it's some number. Okay, so now let's do a linear fit again. Model. Let's do a prediction number as well. That is the predict function. Let's plot Y equal to X. Let's plot the ab line. That's a line like this. And let's just do the line and sort prediction. This is what's going to happen. So So in some sense that it tells you that what is meant by E of the error given X is 0, right? So here the mean is like 50, right? It's a little different from, so the mean is a little different. That's why it doesn't hold for the linear model. And that's exactly what's going on in this whole calculation right here. Right? So this plot tells you that what is meant by E of the mean, the conditional mean of the error given X. That should be 0, and it's not 0. It's coming else, right? So using the quadratic model, if you use the quadratic model, you'll have a black curve like this, and that's a nonlinear estimator, and there's no systematic deviation observation in some sense. So in such a model, the conditional mean of the error given the data set will not be 0. It will vary with X. That's why you get a nice line. Okay, that's the first thing. Okay. So next thing I want to sort of play with is that in this thing is to sort of understand when do I use IIDness, right? So we use the fact that the errors were typically we use the fact that errors are uncorrelated and mean 0. So if I use a normality assumption and independent errors, I want to see what happens. What does it happen? Now, let me again do this. What I'll do, I'll just use a particular data set. So let's say a company cuts jobs periodically, let's say. So every now and then the company will cut, let's say, some amount of jobs by a specific share, and then some are random there's economics influencing it, local politics, and so on and so forth. So how do you, let's do a data set that processes this idea. So first set the seed again, reproduce it again. So I take the date as 51 to 2000, so many dates. That's date now. Let's do date. Let's take date. Date is going to be, so it gives you the entire, from 51 1st January, it just marks all 1st January till 2000. So 50 years there. Then what I'm going to do is, where am I? Okay, I'm going to do is, I'm going to initialize the employment vector. So I'm going to say X is this. So X is this, means I just look at X. It's 5,000 in the beginning, and I'm going to try to see how to sort of. So what I do is I generate a series of observations with random inferences. So what I do is I subtract 50, I add 0.98 times the previous one, 90%, and then I add a simple normal random variable sample with 1 and deviation 200. Okay, that's quite a large deviation. So in some sense, the employment at time t is minus 50 plus 0.98 times the previous year plus a random variable. That's an error. That's how the model looks like. Okay, it's a linear model with this across time. Let's do model here. So we get this. Then now if you do X, and X, it'll show you how it's going. It just starts at 5,000 and it's come down to 511. That's what. So let's just plot this. X is this. Let's just plot it. So here it starts at 5,000 and it comes down to this one. That's how the employment is. So in this case, it's evident that the number of employees cannot be independent example, right? Because every day depends on the previous guy, right? So this is again, this is where the errors are correlated. They're not independent in this model. So that's something you must keep in mind. So this is like if you do linear regression, you will not get the correct answer because everybody is dependent on the previous guy. All the errors that we have, even though I'm generating independent errors here, but they all depend on the previous X minus 1 and X plus 1. So quite cool. So the number of employees is not independent. It depends on the previous. It's correlated with tomorrow's employment in some sense. Right? That's what it's so very good. The last thing I want to sort of play with is that when if I have outliers, how do I handle it? Right? If I have outliers, so you can always get data sets where they have extreme observations. That is, observations that don't fit the general bulk of the data. Right? And then in some cases, you really want to exclude them because you think there's some error in the observation or something's happened. But the least square method is very sensitive to these outside guys, right? So what we'll do is we'll generate a data set, we'll add an outlier, and then we'll try and see how the line changes. Okay, that's what we're going to do. Okay. So what I'm going to do now is I'm going to set the data set C to be this. Right. And first I'm going to generate uniform, and Y is normal. Right? X is around 10 uniform. Let's look at X's. Let's look at 10 uniform numbers between 30 and 70, and Y is normal. Right? Y is normal. So y looks like this, right? So this is the y. Right? So now suppose I plot y and x. Let's see how it looks like. Plot y and x. This is how it looks like. It looks all over the place. It's like some numbers we have. Now what I'm going to do is I'm going to add an extra y. Okay, I'm going to add extra y. Y9 is 2000, so very, very high value, right? Away from 2000. Now let's say go and plot y and x. You look at it, see everybody is here close by on this side, and then the last guy is very, very far. That's 2000. This point, right? That's outline, right? Now, if I go and fit y and x, right? So I'll get some fit, and I fit without the outlier. That means all I do is I just take y without the outlier. I fit that outlier. And then I plot the results now, right? So y and x. So that's, and if I plot the fit with the outlier, let's see what the line looks like. The line will be something like this. Plot without the outlier, the line looks like this. So it does make a huge difference for this whole approach in some sense. So this is one way. This is one way we understand the three assumptions. One is mean zero, one is IID assumption, there's dependency, and the other one is this large outliers. So you must be careful with regression. All the are very sensitive. So plot the data set. There's one key outlier out there in the far away thing. We just keep aware of it and say not work with it.